A 1.80 step, 4-phase stepper motor has a total of 40 teeth on 8 poles of stator. The number of rotor teeth for this motor will be A 40, B 50, C 100, D 80. The answer is B 50. Explanation. Step angle beta equals 360 degree by MNR. M equals number of phases. NR equals number of rotor teeth. Therefore, NR equals 360 by M beta equals 360 by 4 multiplied by 1.8. NR equals 50.
Step angle, beta. It is the angle subtended by rotor position when one pulse is applied to the input of the stator.
The rotor of a hybrid stepper motor is made up of 2 cups, which typically have 50 teeth each. The 2 cups are offset by 1/2 tooth pitch, and the teeth on one cup are polarized north, while the teeth on the other cup are polarized south, for a total of 100 poles, or 50 pole pairs. The advantage of rotor teeth is that an abradable coating can be reliably applied to the stationary component to allow for a tight clearance and to avoid mushrooming of the seal teeth upon rubbing. Which type of motor is most suitable for computer printer shrive? A. Reluctance motor. B. Hysteresis motor. C. Shaded pole motor. D. Stepper motor. The answer is D. Stepper motor. Explanation. Stepper motor is used in typewriters, line printers, tape drives, floppy disk shriver, process control systems and XY plotters. It is a special type of synchronous motor which is designed to rotate through a specific angle, step, for each electrical pulses received by its control unit. Stepper motors convert electricity into rotation. Not only does a stepper motor convert electrical power into rotation, but it can be very accurately controlled in terms of how far it will rotate and how fast. Stepper motors are so named because each pulse of electricity turns the motor one step. Stepper motors are controlled by a driver, which sends the pulses into the motor causing it to turn. The number of pulses the motor turns is equal to the number of pulses fed into the driver. The motor will spin at a rate that is equal to the frequency of those same pulses. Stepper motors can respond and accelerate quickly. They have low rotor inertia that can get up to speed quickly. For this reason, stepper motors are ideal for short, quick moves. 8. In case of an armature-controlled separately excited DC motor drive with closed-loop speed control, an inner current loop is useful because it A. Limits the speed of the motor to a safe value. B. Helps in improving the drive energy efficiency. C. Limits the peak current of the motor to the permissible value. D. Reduces the steady-state speed error. The answer is C. Limits the peak current of the motor to the permissible value. Explanation. Inner current loop limits the maximum value of current, whereas M-loop controls the speed. Closed-loop speed control of DC motor. The converters, rectifiers and choppers are built using semiconductor devices, which have very low thermal capacity. Consequently, their transient and steady-state current ratings are same. The DC motors can carry 2 to 3.5 times the rated current during transient operations of short durations, such as starting, braking and reversing. Higher the current, higher is the torque and faster is the transient response. Therefore, when fast response during transient operations is required, motor current is allowed to have maximum permissible value. The converter rating is then chosen equal to the maximum permissible value of motor current.
Ratio of the rotor reactance X to the rotor resistance R for a two-phase servomotor A is equal to that of a normal induction motor. B is less than that of a normal induction motor. C is greater than that of a normal induction motor. D may be less or greater than that of a normal induction motor. The answer is B is less than that of a normal induction motor. The rotor bars of two-phase servomotor have high resistance so as to have torque-speed characteristics linear for various voltages over a wide speed range, particularly near the zero speed. Hence rotor reactance X to resistance R ratio of two-phase servomotor is less.
The stator of a two-phase AC servomotor consists of two distributed windings which are displaced from each other by 90 degrees electrical. One winding is known as reference phase and is supplied from a constant voltage source. The other winding is known as control phase and is supplied with a variable voltage of the same frequency as the reference phase voltage, but is displaced by 90 degrees electrical.
For a normal induction motor, X/R ratio is high so that the maximum torque is obtained in normal operating region, which is around 5% of slip.
The compensating winding in DC machine. A is located in armature slots for compensation of the armature reaction. B is located on commutating poles for improving the commutation. C is located on pole shoes for avoiding the flashover at the commutator surface. D is located on pole shoes to avoid the sparking at the brushes. The answer is C is located on pole shoes for avoiding the flashover at the commutator surface. Explanation. Compensating winding located on pole shoes is used to nullify the cross-magnetizing effect of armature reaction and hence avoid flashover of the commutator. Large fluctuations in load will induce static EMFs in armature, which aid the generated EMF. This may cause the mica insulation between commutator segments break down, leading to a short circuit of commutator segments. When this process extends to all the segments, it is called flashover of the commutator.
A 4-pole dynamo with wave-wound armature has 51 slots containing 20 conductors in each slot. The induced EMF is 357 volts and the speed is 8,500 rpm. The flux per pole will be A, 3.5 mWebers, B, 1.2 mWebers, C, 14 mWebers, D, 21 mWebers. The answer is B, 1.2 mWebers. Explanation: induced EMF in a DC machine E equals phase Zn divided by 60 multiplied by P divided by A 357 equals Phi multiplied by 51 multiplied by 20 multiplied by 8500 divided by 60 multiplied by 4 divided by 2. Number of parallel path A equals 2 for wave winding. Flux per pole F equals 1.23 milliwebers. Wave winding, the armature winding in which two coils are connected in series and follow each other on the surface of the armature like waves such that there are only two paths for the current flow irrespective of the number of poles in the circuit. For simplex wave winding, the number of parallel paths between the brushes is always 2. For multiplex wave winding, the number of the parallel path is 2m, where m is the multiplicity of the winding. M equals 1 for simplex winding, m equals 2 for duplex winding, m equals 3 for triplex winding.